Hello, this is Jack Jackson, and this video we're going to start talking about rotations. Previously, in the last few videos, we've been talking about uh, translations, which is our first type of isometry that we were going to look at, and rotations will be the next one. In this next little series of videos, we'll be following a format pretty close to the way we did with translations. So, first of all, to understand translations, we had to understand vectors. In rotations, we need to understand the magnitude of a rotation or rotational angle. So recall what we've been doing in this geometry class. We defined an angle as the union of two rays with a common endpoint. Okay, so an angle is a geometric figure, a set of points. In our treatment of Euclidean geometry, we always measure the angle in radians, or occasionally in degrees, but in radians with a number in the interval from 0 to pi, or in degrees from 0 to 180 degrees. And when we get to geometric rotations, and in this part of the course, and in a trigonometry class, and pre-calculus and calculus and so forth, it's useful to extend this idea so we can consider an angle as an amount of rotation, which can have any real numbers to measure. Now that's really two different things. It's more like a different way of measuring angles versus the actual physical set of points, or at least idealized set of points. Okay, so to make a distinction, what I'm going to do is call angles as we've defined them, the union of two rays with a common endpoint, as either angles or physical angles. Okay, and the amount and their measures will be between 0 and pi, but an amount of a rotation will be called the measure of a rotation or a rotational angle. So that's measuring any positive real number there. And informally, we measure a rotation is the sine of a length of it's a signed length of a path, an arc length, taking by a pre-image point one unit away from the center of the rotation, and basically you let it start moving around and tracing out some path. And as you just sort of, just like you had an odometer there, just measure how far it goes. Okay, and if it could go around the circle, well, it could go around more than a semicircle, so it would go out a distance more than pi, and it could go, all the way around the circle. That would be a distance of 2 pi, or even more, so it could have a bigger measure. And if we go in the other direction, we'll call that a negative measure. So let's look at this here. If we've got an angle of 2.1 radians, for example, we can think of this as taking a radius of length 1 circle, and we're talking about taking this, basically sort of taking this ray here and sort of like flicking it, and let it rotate, the whole ray rotate around. Okay, and let's show, let's hide the full circle and just see what happens with that point. As we rotate it around, that point is going to trace out a path there. You see that? Okay, and so the length of that red arc is the radian measure of that angle. Now that's no different than we measured them before, except now we're going to allow this point to not just go to there, it could go even further around. Let's see if this will go bigger than 3, let's say bigger than pi. Let's go 4 radians and see if it'll do. Yeah, so there we go. And so now we can rotate around. Okay, now it's rotating around the shortest distance this way. So this is the way we would do it in our class here. But if we would rotate it, if we'd done that and rotate around this way, we would, in the positive direction, we would have gotten an angle that was bigger than pi, an angle of rotation of 4. Okay, and so that's going to be how we can do that. So in this case, for example, we could have this rotating around here. If we think of it going around the edge of this protractor here, this would be the arc length. So for example, going to here would be 2 radians going around this way. If we went around here, here's 3 radians right about there. Straight out is pi radians. But if we go around here, and we're talking about the arc length all the way around the circle this way, that's going to be a rotational angle, and it's bigger than pi, even though as an angle we would measure it this way. as a rotation, we'll measure it. We could measure it this way because that's the way we did it. We rotated it in that direction. Now we could also rotate in this direction like this, and then we'd be measuring the rotation this way, and that would be a negative angle. Okay. We do say that an angle is in standard position if the initial ray is along the positive part of the x-axis and the vertex is at the origin. And so if we're rotating this direction, the blue one, that's a positive direction. Well, at least it is there. If we're going this way in the clockwise way, that's a negative rotation going from here this way. And if we're going from here, rotating this way, that's a positive direction. So you can start to get this idea about rotations. Okay, so see if we can keep doing this here. Again, talking about rotational angles. Now we can, this one, yeah, this one, I know it's still showing only the shortest angle there. Okay. Okay, so going back that to here, we are defining a Cartesian coordinate system for plane. The angles in standard position if one side, called the initial side, is the same as the positive part of the x-axis and the vertex is the origin. The side of the angle, which is not the initial side, is called the terminal side, and you're thinking about this in motion, right? So if the terminal side has a non-origin point on or above the x-axis, then alpha can be theta plus 2n pi for n in an integer, okay? So what it says is if you think about the theta as being the angle measure the way we do it between 0 and pi, if you're talking about the terminal side being above the x-axis, then you're measuring that angle as theta. If you add any multiple of 2 pi, any integer multiple 2 pi, you will end up at the same place, okay? And you can get all of those measures will generate the same physical angle. If it's on if the terminal side is below the x-axis, then you take the angle and rotate in the other direction. The angle measure would be theta, make it negative though, and add multiples of 2n pi to that, and all of those rotations will end up at the same place. So those are called coterminal sides. A rotation about a point C by measure theta is a transformation. Now we're going to actually get to a rotation transformation. This is a rotation in which transformation in which the image point A prime for a particular image point A has the following characteristics. The distance from C to A prime is the same as the distance from C to A, and the measure of the rotational angle A prime C A is theta, where we're measuring the angle as a magnitude of rotation, rotational angle. The point C is known as the center of rotation, and rotation is denoted by r sub c comma theta. So you give it the center and the angle. And there are many different angles that'll end up with the same amount of rotation, just like we have here. So any alpha in this set right here will all be the same rotation at the end of the day. Okay. So the image of a rotation, think of a turn or spin, might be informal words for that. It's formed by moving each point of the preimage along a path formed by an arc of a circle centered at a given point through a given magnitude of rotation. And points move different distances, but the angle made by the preimage to the center of the rotation to the image is the same as the magnitude of rotation, and at least measured as a rotational angle. As the preimage is placed into motion, it moves from its original location to the location of the image. It always stays on a circle centered at the center of the rotation, so the distance from the center to the preimage point is the same as the distance from the center to its image point. Okay, so here are how we do some compass and straight edge constructions following the same setup. So in order to find the image of our preimage point, the path it takes, we begin by drawing circular arc through the preimage point with center at the given center of the rotation. And we know the image point will be somewhere on that circle. Okay, but we also need to ensure that the image has been rotated through the appropriate angle. So we just need a copy of the angle, so the a congruent angle, so that the copy has the same center, but its initial ray going through the pre-image point and the terminal ray going through the image point. And to do this, we just construct a triangle using the side-side-side property. We've already got the distance from C set out, and we just set the compass and straight edge like this. We set your compass the distance from the center of the rotation to the pre-image point. Make an arc of this radius OA with center and rotation O. You can make the full circle if you want, or as long as you make enough of it to go past where you think the point is going to end up. Okay, it needs, and I would go ahead and make it go through the pre-image point as well. Just make the full circles, okay. And it intersects the given angle twice, and it's long enough to include the image point, okay. So just make a full circle is fine. Notice that the arc you've drawn then, so here it is. Here's an angle right here. There's the center. Let's say it's at the vertex here. And we want to take our pre-image point here. It's going to follow a circular path here from A to A prime, from C to C prime, and B to B prime. Now notice the distance B moved is a lot further than the distance A moved. And the distance, and the point C won't move it at all. I mean the C, but the center of the circle, center of the rotation won't move at all. It's a fixed point. So we take A, put our compass right here at the center, make that circle. So we know A prime is over here somewhere. If we're going in the counterclockwise or positive direction. If we were going in the negative direction, the A would be over this way somewhere. But we want this angle A, center rotation A prime, to be the same as that original angle there. Well, the way you do that is pick a point, find out where just make this full circle right here, and find out where it crosses the angle right here. Well, just measure across here with your compass and measure that circle out from A. Okay, if we were rotating in the negative direction, clockwise, this would be going this way, and it would be this point right there where those two circles meet. But in this case, we're going in the positive direction, so we go in the positive direction, and it's where this circle and this circle here meet, and it's right there at A prime. Why does it work? Well, if you notice, all these distances from the center to any point on the circle are all the same, so those are all congruent. And we've made this third side here of our triangle congruent, maybe not to the other two, but just congruent to the whatever the distance is here. We've made the same distance here congruent. So this triangle here, A, center rotation A prime, versus this point to the center to here, make congruent triangles. And of course, we know congruent triangles have congruent angles, and we get that to work out so that this is the correct angle. We've rotated the right amount. And just repeat that for as many points as you have here, and that will give you this setup. I've got this set up in an older Geometry Sketchpad sketch that I will look at in the next video. Okay, so we'll come back to this again in a bit. And so here's one for you to try. Take this, let's rotate this, and let's say we go in the positive direction. Let's make the center of the rotation the vertex of this angle, and rotate this entire triangle by that amount. Now it turns out to be an isometry. We'll have to prove that later, but since it is an isometry, it's linear transformation, and that means once we get the A to A prime, C to C prime, and B to B prime, we get those 3 points, find their images, a straight edge will take care of getting the rest of the image triangle set up. And so you can see that rotated. You'll see this in motion in the next video. Now, if you have a protractor, it might be a little bit easier. This is just a compass and straight edge type of construction here. But another way we could have done that is just measure this with our protractor, and then use our protractor to measure to get the correct angle here. So you could do that with a protractor, might help a little bit, although honestly the compass and straight edge construction is probably a little more accurate and just as good. We can also do this through tracing. Get some transparent or translucent paper, like for example, patty paper, and trace the pre-image So what you do is here, let's say you put the paper over this. It needs to be big enough to cover the triangle and the point and the angle really, or at least part of the angle here. Trace this on your paper. Put the dot, trace the original ray, which is this one, the initial ray, and then hold your pencil right there at the center of the rotation so it doesn't move. Then as you rotate, make sure that this angle, right, or this side of the angle, this ray, ends up right here on this side. And as you do that, your trace that you have here, you'll see it physically move in motion as it moves across to here. So if you check that out, you now see it dynamically in motion. Okay. So at all times, if you're holding that fixed point in the center, holding that fixed, all these points, will stay. A will stay. A on your tracing paper, your patty paper, will stay the same distance from that center all the time. And when this ray, initial ray, ends up where the terminal ray is, then A will end up at A prime, C will end up at C prime, and so forth. That's a good check for doing, once you do with one of these, say by compass and straight edge, you can check it with some patty paper to make sure you've done it correctly. All right, how about with a coordinate grid? Well, it turns out it's kind of difficult to use a coordinate grid as any help with rotations, but there are a couple exceptions. And one of the exceptions is when the angle is a multiple of 90 degrees. Or multiple of pi over 2 radians. Okay, so for an example, let's rotate the following figure 90 degrees, pi over 2 radians, about the given point. That's a positive 90 degrees. And so the pre-image, let's look at what we've got here. So here's the pre-image, and we're rotating. The blue's the pre-image. This is the image. And we want to rotate it pi over 2 radians. So then you want to make sure that this point, A prime, is the same distance away from the center as A is, and that the angle A to the center to A prime is a right angle. Well, one thing that's nice to know about the angle is because if you go to the center, okay, and you go here to get a right angle is pretty easy because we know something about how the slopes, so we can get these angles the same. And we can get the distances the same because there's going one diagonal there. Okay, and so look what's happening here from C to C prime. Notice this one is, let's see, the original one is to the left, 1, 2, 3, 4, 5, 6, 7, and down 1. This one's going to go to the right 1 and down 1, 2, 3, 4, 5, 6, 7. And so we can see that distance is different than the distance A traveled, but it stays the same distance away, right? Pythagorean theorem, if this is 1 by 7, that's going to be square root of 7 squared plus 1 squared. Square root of 50 is the distance from C to the center, same to C prime. Okay, so you can kind of see how that works. So to get to B, you go left 1, 2, 3, 4, 5, 6, 7, and up 3. And so this will be down 7, 1, 2, 3, 4, 5, 6, 7, and left 3 here. So you can kind of get an idea of how that works there. Okay. So exercise, rotate the red pre-image above 90 degrees about the given point. So continue. So you rotate this one 90, now rotate that one 90 more, 90 degrees. So another exercise, what if we consider rotating the entire plane about a point where the center is through a point called center through an angle of theta, what are the fixed points of the rotation? Let's give the center a name, center C. Through an angle, what are the fixed points? What points don't move if there are any? Okay, how about rotations by 180 degrees? Well, it turns out there's a nice geometric connection for this one. Okay, if we replace both x by minus x and y by minus y, both, we attend, we'll talk about reflections a little bit later and composing these things. But it turns out, giving away a punchline later, it turns out if you compose two reflections about intersecting lines, you get a rotation about twice the angle between the two lines. So it turns out that if you replace x by minus x, you reflect over the y-axis, and if you replace y by minus y, you reflect over the x-axis. Well, doing those two reflections goes twice the angle between the axes. Well, the right angle between the axes. So if you double that, you're going to get an angle of pi radians or 180 degrees, or in other words, a half circle rotation.